Welcome to Let's Get to the Marks, going through an A-level biology question on enzymes, and this has got some graph analysis that's a little bit difficult and a little bit of a difficult calculation. So as always, pause the video, have a go at the question, and then unpause the video and watch the walkthrough. And do that for each part of the question. Use scrap paper, bust out your calculator. Let's go. This first question, 7.1, says explain how the active site of an enzyme causes a high rate of reaction. It's worth 3 marks. What you have to bear in mind as an A-level student, you need A-level terminology. Just doing your GCSE lock and key, substrate fits into the active site like a lock and key is not going to get you the marks. They want to know how the enzyme's active site catalyzes the reaction. How does it speed up the rate of reaction? So what do we know? We know that when a substrate joins with an enzyme's active site, we call it an enzyme substrate complex. That's an A-level term that you learn, an ES complex. You learn about that in A-levels. So you can be pretty sure that that's going to be on the mark scheme. So the substrate fits into the active site like a lock and key if you want to say that, but it forms an enzyme substrate complex. Now, this lowers the activation energy required for breaking up the substrate. However, how do we word that? The enzyme alters its active site's shape to mold to the substrate. And we call that the induced fit theory, and we learn that in A-level. Some GCSE syllabuses, you will also learn that. But if you start talking about the induced fit, that the enzyme's active site actually molds itself so that it better fits the shape of the substrate. And in doing that action, that little bit of kinetic energy weakens the bonds in the substrate. So we need to talk about the bonds in the substrate being weakened. Of course, that means there's less energy to break the bonds, and the minimum required energy to break the bonds in a molecule is the activation energy. So technically, this lowers the activation energy. So the key terms here are enzyme substrate complex, waffle a little bit about the induced fit, say that this weakens the bonds in the substrate, and that lowers the activation energy, and you'll be guaranteed your 3 marks. Let's check out the next question. Okay, so we've got this little question here about the action of the enzyme catalase. I'd say pause the video and read all of this. They've got the method here. The student put 5 potato chips in a flask, added 20 centimeter cubed at 0.5 mole per decimeter hydrogen peroxide. So they've given us those variables that are controlled. We've then got the table of results here, table 5. It's got the different concentrations of hydrogen peroxide followed by the time in seconds for 10 centimeter cubed of oxygen to be released. And we've got a blank column here for the rate of reaction of arbitrary units. Other than the one stated, give one factor the student could have controlled. So they want to know a variable they could have controlled. What have they not controlled about the potato chips? So if you check out the potato chips, what haven't they said that they kept the same? They kept the volume and the concentration of hydrogen peroxide the same, but they didn't control the mass of potato chips. So you either want to control the size or the mass of the potato chip. You might want to control the surface area of the potato chip. So there's all different things that could affect the rate of reaction. Think about the kind of factors that affect the rate of an enzyme reaction. So an enzyme is sensitive to pH. So changing the pH, you want to keep that the same with a buffer solution. And the temperature, you want to use a water bath to keep the temperature the same. Otherwise, that's going to affect your rate. The student gave the maximum rate of reaction a value of 1.0 arbitrary units. Now, this is going to be key in our calculation we're going to do. Complete table 5 by calculating the rate of reaction in arbitrary units in AU at each hydrogen peroxide concentration. Record the rates for the missing column over here. So we've got the rate of reaction in arbitrary units. Now, a real common mistake I'm going to do first. This is what I thought first. Oh, I'm just going to do the concentration over the time to get moles per decimeter per second. But of course, this is wrong. This would give us 0.78, something like moles per decimeter used up per second. But of course, we stopped this reaction when 10 centimeters of oxygen had been given off. That didn't mean that all those moles had been used up. So actually, this is an incorrect way to calculate the rate. Now, this would get you 1 mark if for each of these you said, right, well, 10 centimeters of oxygen divided by the time, 10 over 18, for example, is 0.56. So that means there's 0.56 centimeter cubed given off per second. However, again, this would not get you both marks. This would have got you 1 mark if you did that. They told us that the student gave the maximum value. The student gave the maximum rate a value of 1.0. Now, what was the one happening at the fastest rate? Well, we've got 10 centimeters divided by 6, which was the time in seconds. That is the fastest rate going, and that was at 2 mole per decimeter and 2.5, and that gave us a 1.66. So the 1.66 becomes our maximum value of 1.0. So everything else, once we calculate the rate of everything else, it has to be converted into values where 1.66 is the maximum. So basically you need to do 10 over the time and then divide that by 1.66, because everything is in relation to the maximum value 1.66 equaling 1. So you're going to do 10 over 18 divided by 1.66, 10 over 10, which would normally be 1, but that can't be our maximum value because we've been told the 1.66 is equal to 1. So these are the values you get when you do 10 for the centimeter cubed of oxygen over the time taken to find centimeter cubed per second, and then you make them all in relation, all relative to a rate where 1.66 is actually 1.0 in AU for rate of reaction, and that's going to get you the second mark. So the first mark was quite easy. You just do 10 centimeter cubed of oxygen over the time taken to find out how many centimeter cubed per second, and then the second mark, really, you had to convert using 1.66 as 1 as the maximum value. Right, now we've got to plot a graph. So this is just testing your graph skills, okay? So, let me just, so I'm labeling the axes of the graph. That's always going to get you a mark. But I need to show you how I know that rate would be on the left and hydrogen peroxide concentration would be on the x-axis. So the independent variable is always the first column in any biology table. And that goes on the x-axis generally. And the last column in a biology table normally is the mean, or here it's the rate of reaction. That's the dependent variable, and that always goes on the y-axis. So your dependent variable is always on the y-axis. So we're going to do rate. Oh, and we have to include units, so you won't get the mark. So rate of reaction in AU, and at the bottom, hydrogen peroxide concentration in mole per dm to the -3 in moles per decimeter. So yeah, include the unit so you won't get the mark for the correct axes. Now we need to make a suitable scale. A suitable scale should take up over 50% of the x-axis and 50% of the y-axis, and these should be actually used. So we're going to use 0.51, 1.5, 2, and 2.5. That takes us over halfway up the graph paper. And then when we come up on the y-axis, we're going to just do it going up in 0.2, and that's going to use nearly the whole page. So we're definitely taking up 2/3 or more of the graph paper, so that's good. Now we just need to plot the dots on, and this gets a bit confusing when you're doing it on the PC, because I've got to scroll back up and remind myself of what the blooming numbers are. Okay, so the first plot at 0.2 mole, 0.5 mole per decimeter, I want to go up at 0.33. We calculated that. The second plot at 1 mole per decimeter, we want to go up and put that at 0.6. At 1.5, it's 0.86, so that's 3 mini squares up. Each mini square is worth 0.2 on my y-axis. And then the last two are on 1 and 1. And that's all you need to do to get the 3 marks. I'm going to attempt to put a curve of best fit through it, but yeah, that wasn't very good. Let's try again. Okay, you don't need this for the marks. It just says you need to plot the points of your process data. So they've just given you a mark for the labels with the units, correct axes, using a suitable scale, and plotting the points. And the last part to this question says, suggest a change the student could make to this procedure so that 10 centimeter cubed of oxygen would be produced in a shorter time. How can we speed up the rate of reaction? Well, look, if I went to 3, it would still be 6 seconds. So concentration's no longer the limiting factor. Yeah, we got to a point where increasing the concentration has no effect. So what else could be a limiting factor in a chemical reaction? Well, obviously temperature. Don't forget this involves enzymes though. Surface area. What else affects the rate of reaction? All sorts of things, but that's good enough. pH, because it's an enzyme-controlled reaction, that's going to affect the rate if you're closer to the optimum pH. So I'd say increase the temperature, but be wary not to go above 40 degrees. So if you want to say, oh, do it at 35, say that, but don't say above 40. That's going to denature proteins like catalase, the enzyme in question here. You could change the pH or surface area of the potato chips, but I'm not going with that. Okay, guys, don't forget sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks.
You're still here? It's over.